I will talk about this project that I did in collaboration with Wilmar Cardona, Alejandro Estrada, Soas Nesseris, where basically we mapped the Hortensky theories in effective fluids, so that we can implement this kind of models easily, relatively easily, in Boltzmann solvers. This is the outline of the talk, and so I will start by talking about the standard model a little bit. So as you know, in standard model, general relativity is the theory of gravity that describes theory of gravity. We have the standard model of particle physics, which partially describes the matter content in the universe. We also have an inflationary period and two mysterious components that we call dark matter and the cosmological constant, which made out most of the matter content we know. We also assume flatness usually. We end up with a 6-parameter model that allows us to compute predictions for the observables that, for example, we observe with the Planck satellite or with TES, etc. And we can compare these statistical properties of the model with the observations, for example, as we do the CMB. So Planck, here I showed the angular power spectrum for the CMB anisotropies from Planck 2018. In the red points, you can see the observations, and in the blue curve, you see the best fit for the lambda CDM. And as you can see, the model fits extremely well the observations. However, one has to remember that the lambda CDM model is just a good phenomenological description for the universe, right? So that's the reason why people look for more fundamental theories that explain, for example, the recent accelerating expansion. Here, for example, we have fairly general theory, which is the Hortensky-Lagrangian, right? I don't put the specific conversion functions now, but you're already familiar with that. We know that with the recent discovery of gravitational waves, these kind of theories got simplified, right? Because we know that the speed of propagation is very close to the speed of light. And this puts a constraint on this kind of theories, which as a result get simplified, right? So we end up with this reduced Lagrangian for the Hortensky, which still includes a lot of theories like f of r, KGB, quintessence, k-essence, etc. And that's the kind of models we focus on these projects, okay? And that's the ones we want to map into an effective fluid. So let's first remember what we do in the standard approach, in the standard model, right? So this is the Einstein-Hilbert action. By applying the principle of least action, you can find the field equations, the Einstein equations, right? And we usually also assume that the metric is the Friedman, linearly perturbed, like I'm showing here. We use usually the Newtonian gauge for these perturbations. You can also find the synchronous gauge, but in the code I will use, we have this gauge. Matter is usually described as perfect fluid with small perturbations as well, as you can see here below with the perturbations in the density and the velocity and then isotopic stress. Okay. Then at the background level, with Einstein equations, if you assume the Friedman metric, you can find the usual Friedman equations with H being the Hubble parameter, rho and P the pressure and the density and the pressure for the fluids background level. And if you go to linear perturbations, then you find these equations basically for the evolution of the potentials and the perturbations on the density and the velocity, etc. Right? We can also have the evolution for the perturbations from the conservation laws, right? So here I'm showing the evolution equation or the differential equations for the density perturbations and the velocity perturbations of the fluid, and highlighting the fluid parameters, which are the equation of state, the sound speed, and the anisotropic stress. However, in this form, the equation for the velocity might have problems because of the crossing of the equation of state through -1. But it's not actually a problem because we can redefine the variables in this way so that we have no problems with that. And this is the system of differential equations that the Boltzmann code solves basically, right? So that's we want to map the Hortensky theories into a fluid with this kind of equations, having a particular equation of state, pressure perturbation, and anisotropic stress. Okay, good. So we can start from the action for the Hortensky. Again, by applying the principle of least action, we can find the gravitational field equations, which, by assuming the Friedman metric, look like this. These equations we can rearrange so that they look similar to the ones in the standard model. This we do by defining this effective density and effective pressure for the terms coming from the modifications of gravity, let's say. Okay, so by defining this density, this is effective density and effective pressure, we can also have the first, let's say, fluid parameter for the Hortensky theories, which is the equation of state. Right? Then we are missing just the sound speed and the anisotropic stress for this description. This we can obtain from the linearized gravitational field equations and the scalar field equation. All right. We can rewrite our equations as in the standard model, right, by defining this effective energy momentum tensor. And if you remember the definition of that we are using, we can just extract the information we need, which are the density perturbations, the pressure perturbation, and the anisotropic stress, and the velocity perturbations, right? However, since the theories are complicated enough, these expressions are a bit ugly, right? But we can simplify this by using the subhorizon approximation and the quasi-static approximations. Here, for example, I have the perturbation on the Ricci scalar, and by applying these approximations, we get this expression, this much more nicer expression for the perturbation of the Ricci scalar. So by doing so, in our expressions for the pressure perturbation, the density, the perturbation of the density, and the perturbations of the velocity, we can have these nice analytical expressions for the remaining Hortensky Lagrangian, right? And from this, we can obtain the sound speeds, also an analytical expression for this. And we are just missing the anisotropic stress, which we can get again easily from the gravitational and the scalar field equation. We applied this superhorizon quasi-static approximation. So we have these equations and we solve for the potentials and the perturbation of the scalar field, so that we can have this, and we can also find expressions for the effective Newtonian constant. And finally, we get the expression we needed for the anisotropic stress for these fairly general models, right? So by having the Hort density theory is described as an effective fluid, we can just use the default class version, which is the Boltzmann code that solves the linear perturbations and computes observables like the CMB angular power spectrum, the matter power spectrum, etc. Right? Then, in this case, when the models have an isotopic stress, one has to take into account that the perturbations or the stability of the perturbations are is driven by an effective sound speed, which is defined in this way. Okay, so this is the quantity which has to be positive in this case. Good. So let's go for the results. So by having this, let's say, description of these kind of models, we were wondering if we were able to find a model which have the same has the same background as lambda CDM, but different at the perturbation levels. Okay, so we focus on the KGP models, and we impose these constraints that this kind of models don't have an isotopic stress, and the equation of state is equal to -1. So by doing some algebra with the equations I discussed previously, we can have expressions for the fluid description, which are simplified, okay, in this case. And we can also have, like from the modified Friedmann equation and the scalar field equation, we have these equations here that allow us to solve for a specific form of these models, and we find here. Okay, so by having these particular functional forms, we can implement this in high class, for example. Thus, is a code that solves the perturbations for the Hortensky theories, right? Without using any superhorizon or quasi-static approximations. This code uses a parametrization for this kind of models in terms of alphas, which are given by these expressions here, right? Since we have already a model, a specific model, we can implement it in high class by just replacing our model in the expressions for alphas, and they look, in our case, very simple. This. So what we did is that we implement our model, our design model in high class, which does not use any approximation, and we, with our expressions for the effective fluid description of Hortensky, we implemented in the class code, in the default class code. In our approach, as I mentioned, we use these approximations. Here in the plots, I'm comparing the output from high class and from our code that we call EF class for the large angular scales in the CMB angular power spectrum. And as you can see, the agreement between the two codes is very good, which is also shown in the right-hand side figure. So the agreement is better than 0.3%. Okay, So in this way, we validated the approximations that we employed in our methods. We also did it for f of r models. So the first place we did it for f of r, which also have a background which matches lambda CDM that is has a equation state equal to -1. We implemented in other codes by EFTCAN and class EOS f of r. These codes don't use any approximation as we do. And you can see as well for the case of the angular power spectrum, the CMB angular power spectrum, that the agreement between the codes is good. We also implement the Huon-Sawicki model. And in this case, one has to take into account that the background is not lambda CDM. So you also have to solve the equation for the background, right? So, but usually people don't do that. So in MGCAM and FRCAM, at the time we wrote the paper, they don't use, they don't solve for the background. They just assume that the background is lambda CDM. Whereas in our paper, in our approach, we actually solved the equation for the background. And here we are comparing the output for the CMB angular power spectrum from these codes. And there is some disagreement that we attribute to the assumption that the background in this kind of models is taken as lambda CDM, whereas actually it evolves differently.
Wilmar, you have 5 minutes.
Yes, I'm just finishing. Next thing we did is to compute the cosmological constraints for the 3 models I discussed previously. So we used the supernovae from Pantheon, CMB lensing, and the manisotropies of the CMB from Planck 2018, H0 from Rees, the baryon acoustic oscillations from the BOSS, 6-degree field, and SDSS, and also data from the redshift space distortions. Okay. So what we did is that we compute the cosmological constraints through an MCMC technique by using the code MultiPython and our code, our class code with the modifications, defective fluid approach. And these are the flat priors we use for the parameters. So the parameters in common with lambda CDM, which are the first 6, are the same priors that the Planck collaboration used in their papers. And these are the priors, the last 3 are the priors we use for the modified gravity parameters in the models we study. Good, so these are the results for the designer f of r model, the one which matches the background evolution of lambda CDM with different data. So in all the figures I will show you, the black dashed line, vertical lines, indicates the results from Planck for lambda CDM. And as you can see, all the parameters in common with lambda CDM are in good agreement with our results. For the neutrino mass, which is a parameter we take into account as a varying parameter in our analysis, we can only set upper bounds for this neutrino mass. And for the modified gravity parameter, what we see in our analysis is that it remains unconstrained. So it's basically dominated by the prior. We also implement the Huon-Sawicki model, but the results are pretty similar to the previous case. So all the parameters in common with lambda CDM agree very well with the planned results. And for the neutrino mass and the modified gravity parameters, conclusions are similar for the two FOR models. Finally, here we have the constraints for the, let's say, the designer Hortensky model we cook up. And the conclusions are, as for the FOR models, we cannot say too much about the modified gravity parameters, and we can only set upper limits for the neutrino mass. Interesting, we also were looking for some kind of degeneracies between the neutrino masses and the modified gravity parameters, but we didn't see it in any case. So I guess I will leave you with my conclusions, and that's it.